Welcome to lecture 17 of the course Marine Propulsion. Today we will continue with Hull-Propeller Interaction. So, the key concepts covered in today's lecture will be thrust deduction and relative rotative efficiency in the context of Hull-Propeller Interaction. So, in the last lecture we have seen the main aspects of Hull-Propeller Interaction, that includes the effect of the hull on the propeller performance and also the effect of the propeller on the ship hull. So, the main aspects of these interactions are the wake behind the ship hull at which the propeller operates, and then the propeller accelerating the flow in the aft part of the ship, and the relative performance of the propeller in the open water and behind hull, which gives rise to all these factors that we are studying. When the propeller operates behind the ship hull, it accelerates the flow which is at the stern part of the ship, and this results in the increase of the resistance of the hull. Now, this is shown here as the resistance of the ship, which is the total resistance RTP in the presence of propeller will be higher than RT. So, here RT is the total resistance measured during resistance test. So, if we do a resistance test where we do not have any propeller, then RT is the total resistance. Now, during a self-propelled condition, when the propeller is working behind the ship hull, the propeller accelerates the flow and that causes an augment of the resistance. So, RTP is the case which is the resistance when the propeller is working behind the ship, and that also depends on the thrust loading of the propeller. Now, how does it do it? When the propeller rotates, it accelerates the flow, and also because of that there is a low pressure region in the stern of the ship, and as a result we have a increase in the resistance which is higher finally compared to the calm water resistance that we measure the total resistance in the resistance test of the ship without the propeller. So, delta R is the increase of resistance, let us say for a specific speed. If that is so, delta R will be given by RT P, which is the resistance with the propeller working, minus RT, which is the total resistance at the same speed of the ship. Because of this increase in resistance due to the presence of propeller, the thrust required by the propeller will be more. So, when the ship during the self propulsion test or any practical case when a ship moves forward at the design speed, the thrust provided by the propeller should balance the total resistance in the self propelled condition. Now, that thrust T should be equal to RTP, which is the total resistance of the ship with the propeller working behind. Now, because RTP is greater than RT, which is the resistance measured during the resistance test without the propeller, the thrust requirement should be higher as compared to the actual resistance without the propeller. So, in order to do this, we write T is RT plus delta R. Now, it is very difficult to calculate or measure this added resistance due to the presence of propeller. So, what we do for a practical purpose is we express it as an equivalent increase of thrust. So, if T is the thrust which is required to balance the resistance of the ship in the self propelled condition, then the thrust that is required to balance RT, which is the total resistance of the ship that we measure from the resistance test, should be lower than T by the amount delta T, where delta T is taken to be the same as delta R, which is the increase of resistance. So, instead of increasing the resistance by delta R, what we do is we make an equivalent decrease of thrust. We see it as a loss of thrust, because our thrust has to now cater for the increased resistance in the condition where we have a working propeller behind the ship. So, in order to do that, we say that the thrust is reduced by the same amount by which the resistance was increased. So, T minus delta T is RT, which is the total resistance of the ship that we have measured during the resistance test. Okay. So, now this delta T is obviously equal to delta R, which is the increase of resistance, and the ratio of this delta T to the thrust is called the thrust reduction factor. As we see in naval architecture, we express certain parameters as non-dimensional fractions. Here also we express this change in thrust or the thrust reduction as a fraction of the total thrust and mention it as small t, which is the thrust reduction factor, or in some cases it is also mentioned as thrust reduction fraction. Once we do it, then we can express this thrust reduction fraction as a function of both the thrust and resistance in this form. So, the thrust that is measured in the self propulsion test from the propeller is related to the total resistance of the ship. In the case where there was no propeller, the total resistance from the resistance test using the thrust reduction fraction in this way. So, we can write 1 minus T equal to RT by T, T equals 1 minus RT by T. Here T is the thrust of the propeller which is allowing the ship to move forward at a specific speed during the self propel condition. If there are more than one propellers, in let us say if there are two propellers, then T is the total thrust from the two propellers. So, RT is the total resistance from the resistance test for the ship without the propeller, and T is the total thrust produced by a propeller or multiple propellers depending on the ship design. Okay. And the thrust reduction factor T can be calculated using this expression. Next very important term is the relative rotative efficiency. So, when the propeller operates in uniform inflow, then the flow into the propeller is totally uniform on the entire propeller disc. So, at each point on the propeller disc, the inflow velocity is equal in the open water condition, which is equal to the advance speed of the propeller. Now, when it works in the behind hull condition, then we have seen that the wake velocity of the ship is actually the inflow into the propeller. So, what the propeller faces is basically the nominal wake that we have already discussed. So, in this case, the propeller works in a flow field where the velocities vary in both radial and circumferential directions. Hence, the efficiency of the propeller when working behind the ship will be different from the efficiency in the open water condition. This is mentioned in the condition of behind hull, eta B. So, for the open water condition, eta O, the efficiency is defined in this way: TO, which is the thrust of the propeller in the open water condition, multiplied by advance velocity by 2 pi n, the rotational speed, into torque. So, in the behind condition, in a very similar way, instead of TO and QO, we will be having TB and QB, which are the thrust and torque in the behind condition. So, eta behind here is the efficiency of the propeller working behind the ship hull in the wake of the ship. So, the relative rotative efficiency is defined as the ratio of eta B to eta O. So, eta R is the relative rotative efficiency given by eta B divided by eta O. So, one must understand here that the relative rotative efficiency is just a ratio of two efficiencies. That means the efficiency of the propeller behind hull and the efficiency of the propeller in open water. So, strictly speaking, the relative rotative efficiency is not an efficiency term. It is defined as a ratio of two efficiency terms. So, it is not defined as output by input power, just like, for example, how propeller efficiency is defined in the open water or behind condition. So, each of these terms eta B and eta O are actual efficiency terms which define the ratio of output power by input power. So, these are practical efficiency terms for propellers eta B and eta O, but eta R is just a ratio of two efficiencies. So, it is strictly not an efficiency term. Hence, the value of eta R can even be higher than 1. So, if we see, typically the value of eta R varies from anything between 0.95 to around 1.05 in that range. So, it depends both on the propeller design as well as the hull form design, the stern part of the hull, how the flow into the propeller is happening and how the propeller is performing behind hull with respect to the open water. Okay. So, now if we look at typically how the wake field is for a propeller. This is a nominal wake fraction plotted over the propeller disc for a single screw ship. So, it has only one propeller in the central line of the ship and the wake fraction is plotted on the entire propeller disc. The central part here, the white region, is the hub region where we do not have the blades. So, the wake fraction is plotted only in the range between RB to R where we have the propeller blades. So, here we can see that the wake fractions are very high at the central locations where the blockage effect is highest. So, the wake velocities will be low, which will give rise to high wake fraction, and along the periphery, especially along this region and this regions, the wake fraction value is very low because the velocities are very close to the free stream velocity or the ship velocity here. So, the wake fraction is high in the central region and in the vertical domain here in this region. The wake fraction value is high where the blockage effect due to the hull is maximum. So, this gives an idea of the velocity field which the propeller faces when it works behind a ship. So, if we try to draw a propeller blade here very simply. So, in this particular position it will face the velocity field as depicted by this wake fraction. Now, when the propeller moves, let us say if you rotate the propeller, if it rotates in the right handed way in the clockwise direction. So, when it comes to a position here, the velocity field it faces will be totally different because the nominal wake fraction will be different in this domain. So, nominal wake fraction is what? It is the wake fraction which is encountered without the propeller. So, this is only due to the effect of the hull. So, if we put a propeller blade in this particular location, it will experience this change of velocity over an entire rotation because of the change in wake fraction in both radial as well as circumferential direction. Hence, this gives a picture of the changes in the inflow velocity that a propeller blade encounters over one whole rotation behind the ship hull. Hence, the efficiency of a propeller blade working behind the ship hull will be different. So, when we discuss about propeller design, the concepts of wake adapted design will be discussed. So, basically it is possible to design blades in such a way that they will perform quite good behind the ship hull and they will be adapted to the wake of the ship hull depending on the design of the stern. So, the equation for relative rotative efficiency can be finally written in this form: the ratio of the thrust in behind to open water multiplied by the ratio of the torque in open water to behind condition. Okay. now if we go back to our discussions on thrust identity and torque identity, we get two different conditions. For thrust identity, it was assumed that from the self propulsion test and in the open water condition, the thrust was same. So, Tb is equal to To. If we assume thrust identity, then from the eta r equation we will get that it can be expressed as the ratio of torques. So, eta r will be the open water torque value by the behind hull torque for the propeller. In the same way, if we assume torque identity, that means if we take the torque value equal between the behind hull and the open water condition, then eta r can be expressed as a ratio of the thrust values. In this case, it will just be the reverse, that means eta r will be the behind hull thrust divided by the open water thrust. So, when we do an evaluation of the powering of a ship using the self propulsion test results and open water data, we will use these identities, and in this way we can compute the eta r with the ratio of the behind hull torque or the thrust to the open water values. Now, this will be better explained using a simple problem that we will do now. So, in this problem, what we want to do is, for a given set of conditions, we have to calculate the coefficients. So, we have a ship here which is moving ahead with a velocity or speed 16 knots and a total resistance of 250 kilonewton is given. Okay. Now, the vessel is fitted with a single propeller, the diameter is given and it produces a thrust of 350 kilonewton and the rotational speed is given as 180 rpm and a delivered power PD of 3500 kilowatt. So, basically the operation condition for a ship and its propeller is given, and the open water diagram is also given for the propeller, because we have seen that when we want to calculate all these propulsion coefficients, we need to go to the open water diagram and get the open water thrust and torque coefficients. To mostly the first step will be to get the operation point, because that is where the propeller characteristics will be calculated from the open water. Operation points means the advance speed or the advance ratio J at which we are operating the propeller when the ship is moving at that speed. So, finally, we are asked to calculate the propulsion coefficients, basically the wake fraction, thrust deduction fraction, relative rotative efficiency and open water efficiency. Okay. So, what we have learnt in the Hull-Propeller interaction part, we will be using those expressions and those techniques to work out this problem and calculate the propulsion coefficients. So, these are the input values which are given in this problem. The velocity is converted into meter per second for standard calculations. The n, the rotational speed is 3 rps. The total resistance RT is given, which is the resistance for the ship. This is actually the extrapolated resistance which we get from the model scale to the full scale. So, this is the resistance without the propeller. So, RT is basically the total resistance of the ship alone. So, it is the resistance of the ship without the acting propeller, RT, which in standard way we call the total resistance. PD is the delivered power, 3500 kilowatt. Now, using that we can calculate the torque. So, the torque the propeller will absorb will be PD by 2 pi n, where n is the rotational speed, and we can first calculate the torque as the first step in this problem using the delivered power. The next thing we can compute is the thrust deduction factor, because the total resistance of the ship is given and the propeller is producing a thrust of 350 kilonewton for the specific speed of 16 knots. So, we can use the value of the total resistance and thrust to calculate the thrust deduction factor. Now, to calculate the other aspects of Hull-Propeller interaction, we have to either use thrust identity or torque identity, and in this problem both of them will be used to calculate the factors separately. So, we have the table which is representing the open water diagram for the propeller, and we start with the thrust identity. So, just a brief recap, what is thrust identity? Thrust identity assumes that the thrust produced by the propeller in the behind hull condition is same as in the open water condition for the same RPM, and that leads to the condition where Kt or the thrust coefficient for the propeller is same in the behind hull condition and open water condition. So, if we apply thrust identity, the first step will be to calculate the thrust coefficient. So, from the given value of thrust for the propeller, we can calculate the thrust coefficient based on the diameter and RPM, and we get the value of Kt. As we have seen in the calculation for effective wake fraction, we have to use this value of thrust coefficient to enter the open water diagram, because here Ktb, which is calculated here, this value is Ktb, and we will assume that Ktb is equal to Kt open water for thrust identity. So, we enter the open water diagram with the calculated value of Kt, and with the input Kt we need to calculate the J, which is the advance ratio, and the value of Kq and open water efficiency. So, next we can calculate J for the given Kt. We enter the open water diagram here at the point which is encircled, and we can calculate the corresponding J and the corresponding Kq, and from the calculation of J we can get the velocity of advance Va as Jnd, where the propeller RPM and diameter are already known. So, based on thrust identity, it is the same RPM here, and we can calculate the velocity of advance. Now, once we have that, we can calculate the wake fraction, the effective wake fraction based on thrust identity, because that is the premise of this particular calculation. So, it is given with respect to the speed of the ship and the speed of advance here, and we get the value of wake fraction. Similarly, we can use thrust identity to calculate the KQO, which is the open water torque. Now, because thrust identity is assumed, the open water torque coefficient is not equal to the behind hull torque coefficient. So, from the open water torque coefficient KQO, we will calculate the torque in the open water condition, and the relative rotative efficiency using thrust identity, as we have already seen, is given by this particular expression, and it gives us a value of 1.058 in this condition. And finally, we calculate the open water efficiency from the given value of thrust coefficient. It comes out to be 0.55 using thrust identity. So, in thrust identity, we enter the open water diagram with the calculated thrust coefficient and get the Hull-Propeller interaction coefficients, which is the effective wake fraction, relative rotative efficiency, and also the efficiency of the propeller in open water eta. Next, we will use torque identity. Again, what is the assumption in torque identity? That the propeller has the same torque in behind hull and open water condition when having the same RPM. So, just the inverse way here, instead of thrust, we will enter the open water diagram with the torque coefficient. So, the first step will be to calculate the torque coefficient Kq, and this is Kqb, and we will assume that Kqb is equal to Kqo as per torque identity, and we enter the open water diagram with the torque coefficient in the torque identity. So, the calculated value of 10 kq is taken here on the curve for the 10 kq, and corresponding to that point we get the value of j and also get the value of kt and eta O. So, in a similar way we get the value of the advance coefficient and KTO, and from the value of j we calculate the advance speed, and finally from the advance speed we use the value of ship speed to calculate the wake fraction, the effective wake fraction by torque identity written as W with a suffix q, and we see that the value is slightly different from the value obtained using thrust identity. Now, this is based on the problem values which are given for the thrust and torque of this particular ship propeller combination. For an actual case, the differences may be slightly lower between the values obtained by thrust and torque identity. Now, in general, when we do self propulsion tests, the thrust identity is used to calculate the propulsion coefficients. So, moving ahead, we use the same way to calculate the value of the open water thrust coefficient from the open water diagram, and from that we calculate the open water thrust TO. The RPM and propeller diameter are known. This is under the torque identity, and we see that now the relative rotative efficiency, because we have assumed torque identity, eta R will be expressed as a function of the behind hull thrust divided by the open water thrust, and we have a slightly different value of relative rotative efficiency here. And finally, the open water efficiency, once we know KT and KQ, can be computed. So, this is the result from torque identity. So, this problem gives a basic idea of calculation of the Hull-Propeller interaction coefficients and efficiencies using thrust identity and torque identity. This will be all for today's class. Thank you.